Hey guys, so I thought I would just do some really quick, simple proofs of some algebraic operations. I've been doing these in class. Thought I would share them. They're fun. If you want to pause the video at the beginning of each one and try and do it yourself, I encourage you to do so. I'm not going to state all of the axioms and theorems that I'm working with, because those are different from course to course and who you're learning it from or where you're learning it from. I'll just, basically state my reasons for each statement, basically. So the first one, we're going to prove that for any real number, that 0 times 0 is always equal to 0. So if you want to try and do it yourself, go ahead and pause it. I'll wait a second. Alright, so let's start with some axioms that I have. The first one being a times 1 always equals a. I've already proved that. I know it to be true. Second, 1 plus 0 is always going to equal 1. So, as my proof, I'm using a particular axiom, which is the definition of 0, which says that a plus 0 equals 0 plus a equals a. It doesn't make it non-rigorous that I'm using 1. Since both 0 and 1 are unique, it's fine. So we're going to substitute, let's go ahead and number these. So I'm going to substitute 2 into 1. So a times 1 plus 0 equals a. Then we're going to use the distributive property. So a times 1 plus a times 0 equals a. So we've already stated that a times 1 equals a, so we can simplify this further and say a plus a times 0 equals a. And the only instance in which this is possible, which you could also call the uniqueness of 0, so any number, or if a plus any number equals itself, then that something must equal 0, in which case a times 0 equals a. For the next one, we're going to prove that if a is less than b, it implies a plus a constant c is always going to be less than b plus a constant c. Our given, we're going to go ahead and write that down. Per the definition of less than, that means that b minus a must be an element of the real numbers. So for this one, we're going to use the contrapositive. So if p then q is logically equivalent to if not q then not p. So we're going to flip this around and follow that logically and show that its conclusion is the opposite of this, which is that b is less than a. And if b less than a follows from b plus c is less than a plus c, then we know the original if p then q statement is true. Once again, going to use the definition of less than. So a plus c minus b plus c must be an element of positive real numbers. So we're going to use associativity here, or I'm going to switch them around first just to show every step. And then we'll use some associativity. So a plus c minus b should also be in the real numbers. And I didn't state it as a given, but we know that any number minus itself is always going to equal 0. So we can simplify this further and say a minus b must also be in the real numbers, and using the definition of less than. And if a minus b is an element in the real numbers, then we can use the backwards definition of less than to say that b is less than a. And since this is not p, the opposite of this, that means that the original statement if p then q is true. So, proof by contradiction, a plus c must be less than b plus c. Alright, next I'm going to show that if a is an element of the real numbers, or positive real numbers, it implies that negative 1 times a is an element of the negative real numbers. Let's go ahead and write down the given. My support for this one is just a proposition that says the opposite of a is a negative of a, that is negative a equals negative 1 times a. Alright, so if negative a equals negative 1 times a, negative a is an element of negative real numbers. It's a lemma that I have. If a is an element of r plus, then negative a is an element of r minus, and if a is an element of r minus, then negative a is an element of r plus. So there we go. If we substitute 2 into 3, we have negative 1 times a is an element of the negative real numbers. Alright, so our next one here. So we have a conjunctive syllogism. A is less than B and 0 is less than C. It implies that A times C is less than B times C. Let's go ahead and work with this a little bit. We'll write this down as a given. A is less than B. And by the definition of less than, that means B minus A is an element of the positive real numbers. And if 0 is less than C, that means C is also an element of the positive real numbers by the rule of trichotomy, which says that any number falls into only one of three categories. It is 0, is a positive real number, is a negative real number. So on this one as well, we're going to use the contrapositive to prove the original statement. So contrapositive is going to be BC is less than AC. And just like last time, we're going to use the definition of less than. So AC minus BC must be an element of the positive real numbers. We're going to factor out the C, or reverse distribution, whatever you want to call it. So we have C times A minus B. If the product of these is an element of the positive real numbers, that means both A minus B and C must be elements in the real numbers. So we'll go ahead and write that down for redundancy's sake. So we're going to use the reverse definition of less than again, which means that B is less than A. And that is a contradiction with our original statement. And since this is a conjunctive syllogism, that means both have to be the case. And if one is not the case, then the statement is false, which confirms our original statement. And our last one for today. So if A times B equals 0, it implies either A equals 0 or B equals 0. So we have a disjunctive syllogism. So all we need to do, well, sort of, is prove that A is 0 or B is 0. We don't need to prove that either is the case because we know that that's not the case. This one's a little bit longer than the other ones. So this is a theorem that we already proved. We know that any number times 0 is going to equal 0. And our given is A times B equals 0. So this is already looking pretty good. So this is a number theorem, the law of inverses. So if we have B times 1 over B, that will always equal 1. We also know that any number times 1 will always equal itself. We also know that any number plus 0 will always equal itself. So we're going to substitute a couple of these in here. A times B times 1 over B, which we know is 1. So we're substituting into this here. And we know that equals A times 1 is equal to A, but A is also equal to A plus 0, so we're going to use that here. So we're going to use some associativity here. So this is going to be equivalent to A times B times 1 over B. It's going to be 0. So of course we had to assume that in this case B is not 0. So otherwise we would not be able to divide by 0 in this environment that we've created or in general. So this gives us, since A times B is 0, we have 0 times 1 over B is A plus 0. So once again, we're compressing all of this down into 0. Any number times 0 must equal 0. So now we have 0 for the left-hand side, and that equals A plus 0. And any number plus 0 still equals itself. So we have A equals 0. So we would also, there's multiple cases to this, so either A and B are 0, in which case you wouldn't have to prove anything, or show it, I should say, or A equals 0 or B equals 0. Now to be completely 100% rigorous, we would have to do all of this over again, but for B, and we would assume A is 0. So I hope these were interesting or entertaining or helpful to you. If you guys like this, I can do more in the future that get a little bit more complicated and involve some geometry and some other stuff that I'm going to deal with. But thanks for watching. We'll see you next time.